Okay, so I think I can start. So hello everybody, and thanks for staying with me here. And okay, so my talk is supposed to be half a talk and half a tutorial. So there's a small notebook that you can try to play with tensors and also tensor decomposition. So if you check my username on Twitter, there is a Twitter with the link to the presentation, so you can follow the presentation also by downloading it, okay? And there are also links for the notebooks and also things that I'll be using during the presentation. So I'll do the first part with all the math for everything that you have to know about tensors and tensor decomposition, and all the math for unsupervised learning using tensors as input. And then I go to something more practical by using tensor decomposition on wearable sensor data. Okay? So a bit about where I come from. So I'm from Italy. I'm a researcher at the ISI Foundation, Institute for Scientific Interchange. This is a research institute that is based in Italy. And we are also opening offices here in New York, right in front of Bryant Park. So if you want to visit us, we are there. And we are a leading research institution on complex systems and complex networks. And my lab, the data science lab, we try to work in the intersection between complex networks and complex systems with the data science, okay? First, to start a small survey, like how many of you already used the matrix factorization here? Okay, a lot of people already. How many people here used the tensor factorization already? Okay, some people already. And how many of you who used tensor factorization use it with MATLAB? I think it's more or less the only option that you have for tensor decomposition, okay? So the idea is, matrix factorization is already used in many fields. Tensor factorization is I'll be doing a lot of parallels between tensor factorization and matrix factorization because they are very similar. And also tensor factorization is becoming very popular for other types of analysis. It is very useful also to explore temporal graph data, and this is the example that you'll be doing at the end. Still, the most used tool is MATLAB, so the purpose of this talk is also bring new tools for tensor factorization for the Python community. And yeah, for these libraries that I'll show you, there's a lot of room for improvement. That's, yes?
So insofar as the canonical use case for matrix factorization and tensor factorization, like it's a proxy or a way to get like singular values and principal components and things like that. Is that where, like once you have those things, then you can learn from them and tensor factorization is the way to get there? Or is there another?
Yeah, I'll show you during the talk, but yeah, we'll arrive to this. I'll show you all the math to arrive to the components and everything. And also it's important to know how it works because so you can use also the results of the factorization for something useful, right?
Well, when you say on the first slide it's used in many fields, is it just used to get those principal components and singular values, or is it used for something else that I'm not touching on?
A lot of things. So for example, just to start from the beginning, like from the origins, matrix factorization has already been used by this guy that you probably know. It's, his name is Charles Spearman. And he was using, he was applying different intelligent tests of intelligence to different subjects. So you can form a matrix of subjects and the results of the tests. So his idea is that he could factorize this matrix in two different matrices that I'm calling W and H, where you have for different tests what is the intelligence factor that is associated to it, and for the different subjects what's the weight in different intelligence factors. Okay. Jumping back to more recent years, you have an example yesterday also, a lot of people talking about clustering and topic modeling. And if you think about topic modeling, you are just trying to associate different documents to topics, and also the different terms, different topics, okay? So the idea is that you can also use matrix factorization for this. So you have the matrix of documents and terms, and you have two different matrices of documents and topics, and terms and topics. The difference is that these documents and terms matrix is very sparse, okay? And okay, so the problem that you are trying to solve, you are trying to find two different matrices, W and H, where in this case, since we are talking about topic modeling, the values that you have both for the documents and terms matrix are positive values because you have counts of terms. And also for the documents versus topic, you want to have a weight for each one of the documents that you want to associate to a topic, and also for the terms. Okay. So about this non-negative matrix factorization that you can use. What's the problem that you are trying to solve is trying to find these two different matrices, W and J, by minimizing this difference between X and the product of the two matrices. And you use this thing that is the update, like you find the matrices W and H by this iterative update that is called multiplicative update. This is the way that is normally solved. You have different solvers also that are a bit faster than this. And if you compare, for example, non-negative matrix factorization with PCA, for example, that is another way of decomposing a matrix in different matrices. You'll find that for example, if you have a matrix of images versus the pixels of the images, and you're trying to decompose this matrix, what you'll have in the matrix H are the different parts of the faces. For example, I'm trying to factorize images of faces, so you'll have different parts of the faces. And you can represent each one of the faces as the sum of the different parts of the faces. So you have interpretability on this decomposition. This is something that you don't have normally in the PCA. It's very difficult to interpret what you have in the results of the PCA. And there is also a paper, interesting paper, if you want to check, that shows that non-negative matrix factorization is equivalent to spectral clustering, where you have a sort of soft clustering on the data that you are trying to factorize. Okay. So just to give you an example, using scikit-learn to decompose the data set with the digits data set of the scikit-learn, I'm decomposing here in 10 different factors. And you can see that the results of the matrix H, that are the components, are sort of parts of digits that you have in parts of handwritten digits, okay? So next step, what about you don't have matrices, two-dimensional matrices like, so far I was talking about these two-dimensional matrices. But what about if your data set is not a matrix? So a good example is if you have, like for example, these environmental variables, where you have for each location, for example, supposing that you are analyzing the environment, you have different locations, and you have for each location at different time, you have different variables, like for example, temperature, humidity, and things like that. So this you can represent as through a tensor. There are other things that you can represent as as n-way tensors, like other areas like sensory analysis, process analysis, spectroscopy. This is called multi-way data analysis, or multi-way factor analysis. So as you can imagine, with the Internet of Things, you have much more data of this type where you have a multidimensional, many dimensions on your data. You can have, for example, user positions, time, and other variables that you are measuring with your sensors. Okay. Examples of things that you already have published and also being applied in the industry. A nice example is chemometrics, where you have different samples, chemical samples, and for each sample you apply, like you compare the excitation and emission of different types of different samples that you have, and from this, using tensor factorization, you can make a decomposition of the different samples in the compounds of a solution. Okay. There are many different areas like neuroscience, signal processing, computer vision, SNA also, and etc. So for all of this, we are going, in the place of using matrices, we are going to use tensors. Okay. So what is a tensor? A tensor is just a multidimensional array. So for you who work with Python, you already know what is a multidimensional array. For example, a three-way tensor. You have 3 modes. In this case, just this example. Other names that you'll find in the literature on tensors, you have the fibers that are the different slices when you fix 2 different, for example, in 3 dimension, if you fix 2 indexes and make a slice in one of the directions, you have the fibers. And if you fix just one dimension, you have the horizontal, lateral, and frontal slice. Some important operations that you can do and with tensors is the matricization of a tensor, where you can convert a tensor to a matrix. So, for example, if you choose one dimension of your tensor, you just take the slices in that dimension and transform it in a matrix. So this operation is called matricization. And also vectorization, it's like the flatten on Python, on NumPy, okay? You just transform your tensor in an array. So to give you an example of what is unfold operation on a tensor. So I have this tensor here that is a three-dimensional array. And if I do an unfold in the first, in the dimension 0, you have a matrix that is 4 times 2, that is 3 by 8. If you choose the second dimension, you'll have a matrix that is 4 by 3 times 2. And if you want to unfold in the last dimension, you have a matrix that's 2 by 3 times 4. Okay, so just to show you a small code on how you can implement it in Python to do this unfolding on the tensors. Okay. So this is an important operation, and we will use later for the factorization of the tensors. Another important thing is to know what is the concept of the rank of a tensor. So, for example, if you have 3 vectors, A, B, and C, with these 3 vectors, you can produce a tensor by the outer product of these vectors. Okay, so you have the general. So for n dimensions, you have the outer product of the n vectors, and you have an n-dimensional tensor. For 3-dimensional tensors, you have with 3 vectors you can do it. So if A is size n, b, m, and c, t, you have a tensor that is n by m by t. Okay. What is the rank of a tensor? So every tensor can be written as a sum of rank 1 tensors. So if you take many vectors, like in the way that I'm showing the figure, and you sum, you produce the different tensors, rank 1 tensors for these vectors, and you sum them, you'll have a new tensor. Okay, and every tensor can be written in this way. So, for example, I'm showing you here an example of n dimensions, a tensor with n dimensions. So you have a to 1 to a to n. And as you can imagine, if you concatenate each one of these a's, you'll have a new matrix. Okay, so these matrices, a1 to an, we call them the loading matrices of the tensor. Okay. So you can represent, as the last example, a three-way tensor. You can represent it as a combination of three different loading matrices. Okay. So just an example of how you can do it with three different matrices and produce a three-way tensor. This representation of a tensor as three loading matrices is called the Kruskal tensor. And you can do I'm showing you two different ways to produce it in using the three matrices. One using loops and one using the Einstein summation that is available on MyPython. Okay. So about tensor factorization. So it is called in literature Kandacom or Parafac. You can see it as an extension of SVD, MPCA, or non-negative matrix factorization of matrices for tensors. And if you go, for example, from NMF to NTF, that is the non-negative tensor factorization, you can decompose a tensor that have non-negative values to a sum of n, r, non-negative rank 1 tensors. So when you try to decompose this, you are trying to solve this problem. That is trying to find the three loading matrices, A, B, and C, that are non-negative, that minimize the difference between the tensor and the Kruskal tensor of these three matrices. Okay. So how we can perform this tensor decomposition? So there is a very interesting thing about tensors that you can compare, like the unfolded tensor in the kth mode can be represented as a combination of the three loading matrices that it's represented by it. So for example, if you take the tensor and unfold in the first dimension, you'll have the tensor, that the tensor is the product, this operation between C and B, that is the categorical product between C and B. Okay, so you have this equality in the three different ways that you extend, that you unfold the tensor. So as you can imagine, knowing this, you can use everything that you know about matrix factorization now for tensor factorization, because you have everything here. Once you unfold the tensor, you have everything is a matrix. So you can use all the tools that you used for matrix factorization to do tensor factorization. Okay, so in this case, what you are trying to minimize is the difference between the tensor unfolded in different dimensions with this operation of the dot plus Kruskal plus categorical product between the matrices. Okay. So I've just put like side by side over there in the right the things that I've just shown you, and also what we were trying to minimize in the matrix decomposition, that is this X minus WH, this product. And you can see that you have a parallel between these two decompositions. So while in the matrix decomposition you have X, now I'm showing the tensor unfolded in different dimensions. And W and H you can see as A, B, and C, and H as the cathedral product of the different matrices. Okay, so for example, in this code, I'm showing you how you could do this factorization. So one important, if you use the same multiplicative update solver that is used for the matrix factorization, you'll have to make a product of your data with the cathedral product of two matrices. So it's very important to have these two operations very efficient. That is the unfolded tensor times the cathedral product of two matrices. And then it's very important to have to be very fast, that the last operation should be very fast. So you can use, for example, for the multiplicative update, if you want to converge fast, it's known that a multiplicative update doesn't converge very fast, so you can use non-negative least squares to converge faster to a solution, okay? So just to give you an example on how to interpret the three loading matrices of your tensor. So you have just an example, a matrix X with users, terms, and time. And you represent like for each time you have which terms a user is using in that interval of time, okay? And if you factorize it, you'll have three different matrices, A, B, and C, where the matrix A is just a matrix of number of users times number of components that you are factorizing. So you have association of users with different factors. Then you have the terms, that is m terms by k factors. So it's the relation between the weight of each term in the factor. And then you have time in the factors. So if in the matrix C, in this case, it shows the time activity of each one of the factors. So you have by free all this information that is relevant if you want to do visualizations like this, for example. So in this case, we factorized a big data set of 14 million tweets during the Olympics of 2012. And you show the different streams that are the factors or the topics in this case, because we are using for topic detection. And you have the words that are the terms that are present in the factor. And also for each time interval, we count the number of users that you are in that factor.
How do you come up with the topic?
It's unsupervised. So each topic is so you have if you go back in this example here, you have a matrix that are the terms by the factors. So for each factor, you have a vector of terms. Yeah. If you sort these terms and take the nk, the top k terms on. So in this case, I'm taking just the top, the term that is most representative on this vector. Okay. Okay. So tools that you can use for tensor decomposition, of course, you can use MATLAB. This is the most used. Okay. Then you have all the things that you can find in the Python world. Some libraries like scikit-tensor that you can use all the operations that I've shown you, and also some code that you can find online on these links. So let's go to the last part, that is a demonstration of how you can use the tensor decomposition for the composition of wearable sensor data. So in this example, we are using a data set that was collected by this platform, that is the Sociopatterns platform, where we use active RFID sensors to collect social interactions between people. So if a user uses this badge that is an active RFID sensor on his chest, for example, when two people are in front of each other, they exchange information, the tags exchange information, and then you have proximity information between people. So how it works exactly? So you have these people with tags. So if two people are in front of each other, so the tags exchange information, and then you can send this information to an antenna. And this antenna can send information to a server, for example, and you can see in real time what are the social interactions that you have. You can this platform also works like each sensor can also store information about the social interactions on itself, and then you can post-process the data. And for the post-processing and everything, we are using Python everywhere. Okay. This is an example of a primary school where you collected the social interactions in a primary school. This is another primary school in Hong Kong with 900 students. And you have many experiments around the world already, 7 years on doing these experiments. So as you can see, many of these institutions, they are related to health, because why there are many institutions that are related to health, because they want to collect information to understand how the social interactions impact in the spreading of diseases, for example, in a hospital or so on. So let's use tensors again to represent this data.
Who's that guy? Is it a red guy?
It's on the History Channel, I think.
Is that drunk history?
Yes.
The guy that thinks everything is aliens' fault.
Yes, exactly.
This case is all tensors.
Okay. So how you can represent these graphs as three-way tensors? As you know, you can represent a graph as a matrix, the adjacency matrix of the graph. Then if you use time, for each interval of time, you can create a different adjacency matrix for it. And then you have a tensor, okay? So how it works in the case of our experiment, our example. So you have this temporal network that is represented like a tensor representation. Then you use tensor factorization to factorize different loading matrices. Then you have the factors at the end. These are A, B, and C matrices. And as you can imagine, since you have like a matrix in the A and B dimensions, they have the same number of elements, and also these matrices are symmetric. So you can use both A and B to get the like the communities or the groups of each one of the nodes. Okay, and then in the matrix C, you have the temporal signature of each one of these components. Okay, so just to give you an example on the data of the school, if you decompose this data, you have these sort of, each one of the S's are different components. You have 14 components. And the nodes are sorted by class. So you can see that the nodes are grouped by classes. This is automatic is totally unsupervised. So the algorithm doesn't know what is the class, but it comes up with the classes. And you can see that you have also other components that are mixed classes. And if you go to the temporal signature of each one of these components, you'll see that for each class you have the morning and the afternoon. And then for the mixed classes, you have the breaks. Okay? So this is all automatic from the decomposition, all unsupervised. The nice, interesting about the non-negativity of this decomposition is that you can really interpret these factors as things that you see in real world. Okay. So I prepared a small notebook to show you how you can do, or if you want to try this data set with decomposition. I don't know if I have time. 5 minutes. So I think I can show you very fast. So if you go to that okay, so this is the notebook that you have in GitHub. So first thing are just like importing boilerplate and things like that. I'm using this scikit tensor with the operations that I need. Some code, this NCP is also on GitHub repository with all the operations, all the functions for minimization and all non-negative least squares optimization. Then this is the data set. This is one of the data sets where you have the different classes for each one of the nodes. So I have 241 nodes, and for each node I have a different class. Then this is the real data, where you have for each one of the nodes, you have I and j as the index of the node, and t is the interval or the time in seconds when you see that node in a contact between these I and j nodes. Okay. So in this data set we have around 18 hours, and if I show you what is the how many contacts you have in time, you can see that there is a break here in the middle. It means that you clip the night. So these are 2 different days. In the middle you have the night, but it's clipped. And then you have the second day. Okay? So, okay. Here I'm going to create a tensor with, I'm dividing the data set in 150 intervals. So you have a tensor of n nodes by 150. Okay, so this is my tensor x. Then I'll do the decomposition using this non-negative tensor factorization with this method that is non-negative least squares with the block principal pivoting method. Okay, this is available on this on GitHub, on this repository. Okay. Then I have as this x approximate. This is a cross-call decomposition where you have the A, B, and C matrices. Then if you try to plot what you have in here, I'm plotting what you have in A, you can see that if you group by the different classes, you can see that you have 14 components, and for some of the components you have the classes, and others are the mixing of the classes. If I just sort okay, this is the activity that you have in the C matrix. So for each one of the components, you have 150, an array of 150 values, and this is the time signature of each one of the factors. So just to show you reordering of it, if I show you in a nice order that I've chosen previously, so you see that you have all the classes, and then you have some factors that are mixing of classes. This is the time signature, temporal signature of each one, and you see that for the last four ones, you have the breaks. Okay. Okay, that's it. I wanted just to show you, for example, if we want to use one of the matrices as, because since we are using tensor decomposition, as you know, you can use matrix decomposition for dimensionality reduction. You can use also tensor decomposition for dimensionality reduction. So for example, I'm creating a classifier. This is a random forest classifier, just filtering out the teachers because they are much harder to classify and classifying just the students. And if I use the original tensor to classify it, so for each node, I'll have n, an array of n, where n is the number of nodes with all the connections. So if I use this information, I'll have an accuracy in this case of 0.95. But if I use just the A matrix that I got in the decomposition, I can have a higher accuracy just by using this A matrix on the training. If I use both A and B, I think I don't get much more. So you can see that by just using one of the loading matrices for the classification, you can do a good job. Okay. Okay. So just to end up. Yeah. So I just wanted to these are our most powerful learning models. So I would like just to thank them, and these are the group of people that are working on this. And that's it. Thank you.